Good morning, everyone. So we'll finish this lecture first by looking into the end of the proof of the main result of yesterday. So recall that we want to prove that the main theorem was that the classification risk is we characterized it, the minimax rate, and showed that we want to show that it goes to phi bar of B, okay? Where recall that this class is the class of signals that are sparse and that have the non-zero coefficients which are above a certain value, okay? So we defined the class by saying that if I'm in the support of theta I is larger than the oracle threshold plus B. Okay. So that was the definition of the class. And to prove this, we saw that we use a classical technique, which is that we bound from below the minimax risk by a certain Bayesian risk for well-chosen prior pi. Okay. And the prior pi was built as follows. We split the indices, so the integers between 1 and n in Sn blocks. Okay, so that's the first block. Q is, I assume that n over Sn was an integer, just to fix for simplicity, but otherwise it can easily be adapted. So here we have Sn blocks, okay? So Q1, capital Q1, capital Q2, capital Q Sn. And the prior is very simple. On each block, we put zeros except at one place, which is chosen randomly. It's some index, capital I, okay, indexed by the number of the block, okay, etc. Right? So we saw that we had this bound from below just by computing the base risk, and by using this property that the L value procedure is a Bayesian optimal procedure here for the base risk, we had this expression, and we just finished yesterday by computing the L value using Bayes formula. Okay, and we had this expression here. So I'll still make it slightly more compact. So here this is a function which is a certain function h xi a, and it's easy to compute. Okay, it's just the exponential a xi minus a squared over 2, and in particular it's increasing in xi, which we'll use in a moment. And I write it this way because if you want to prove this for other noise distributions, you only need actually the monotonicity here. Okay, so now we just need to compute this M1 quantity. So let's do that. So that's not very difficult because we have some symmetries in the prior. So we have independence. We have defined the prior independently over each block. So in fact, this sum we are now going to split, and it will be there will be a factor Sn which will come naturally, which will be the number. So here I just split the sum I in Qj p pi I equals to ij, and h. So here I just rewrite a little bit the expression. So 1 minus li. So I can pull it on the other side. So it's equivalent to have this in terms of h smaller than a half, and the sum for k in Qj and k. Okay, so h xk a. Okay. All right. So this is just a rewriting of what was there. All right. So that I can also write as I say that it's larger than this double sum p pi I equals to ij, and now it's enough that the number of k's, so the cardinality, let me write it, cardinality of the set of indices k in the block J minus I. So here among these I have one I, that this is, so this is number of indices such that hxka is larger than hxia. Okay. This cardinality is at most 1. Okay, so why is this? This is because, so here I have one, among this sum I have the index I, so I can put it on the other side, and then I just need to, so if I put it on the other side, I get this thing here with k different from I. So we see that it is enough that there is at least one of these h's which is strictly larger than hxia, such that we have that. Okay? So if there is at least one, then a fortiori, since h are all positive functions, this will be true. Okay? And now I can use symmetry. So you see by independence I can put Sn, and here I have a sum. But this sum, actually, since the index capital I is equidistributed, it's a uniform distribution over integers in the block. I can also write this with respect to just index. So the indices don't matter. I can assume that actually it's the first index that has been picked. So namely, so if capital I1 say is 1, then x1 is drawn according to phi a, and I just rewrite what's over here. So with the index 1. So now look at the first block, and the number of other coordinates here. So xk larger. So here I use that. So since h is increasing, so here I use symmetry and the fact that h dot a is increasing. So xk here larger than x1, and hk, since it's not x1, it has been sampled according just to the noise. Okay, so it's epsilon k, and this has cardinality. Cardinality of this is at least 1. Okay, so here you see that we have now a purely a lemma purely on Gaussians. It becomes easy because, so here I said I have just epsilon k, and this x1 is nothing but epsilon 1 plus a. So here I'm just asking what is the probability that if I have n IAD Gaussian noises in the first block, so they are n over, so here the cardinality of this is n over Sn minus 1, okay? So of order n over Sn. So if I have of order n over Sn independent Gaussians, what the probability that there is at least one that is larger than this? So essentially it should it should be that the maximum of this is larger than this. So it's if epsilon 1 is say it is like a OP1, so you just get the probability that the max of Gaussians is larger than A essentially. Okay, so there is a little lemma, which is an exercise, which is that this quantity is actually, so if I call this, so the maximum of Sn, n over Sn Gaussians is of the order square root 2 log n over Sn, so that's where this comes from, okay? And this is just, the lemma is just that if I write, if this is this, the lemma says that this is actually phi A of an star. So if an star is this the oracle threshold, and so A is an star plus B plus little o of 1, and this is, so by definition, this is the same as phi of minus B plus little o of 1, and this is phi bar of B, okay, as we want it. Okay, so that proves the theorem for the classification loss. So the idea is that the idea of the proof is that you split in different blocks, in Sn blocks, and you have the difficulty of each block is characterized by this phi b. So the problem can be the difficulty of the problem can be split in Sn bits, and that's why we get the risk Sn times. So here I forgot Sn, so it's divided by Sn here. Okay, so which is over there, the Sn here. Okay, so this is quite relatively simple proof. So for multiple testing risks, it's harder because you have ratios of random variables, and you have to replace the classification loss by a weighted classification loss to solve the multiple testing problem. Okay, so you have a similar result also for a weighted loss. Okay, so I put that in the notes, but it's you can use similar idea. It's a bit more technical, but you can do that. Yes.
So this prior which you constructed there, so which is bad, but in a certain sense it's really bad because it's clear that it doesn't have enough randomness, because it's so that on every subinterval you always have at least exactly one populated item. So
yes.
So it's not kind of not a good. It's kind of very intuitive that it's not good prior.
Yes.
From the beginning, because you're making you're putting in a certain sense unadmissible knowledge into this.
Yes, so in a sense, this the priors that come in the lower bound proofs, they are very different in spirit. They are just technical tools. They are very different in spirit from the ones we want to use in practice, in a sense. So here, they are just technical devices that we use to bound the minimax risk from below. And indeed, what the philosophy of this choice of prior is just that, okay, so suppose that actually I give you the following problem. The Sn is just 1, and I mean, it's a bit of the same problem. If Sn would just be 1, I would already have to solve the problem if I have n prime equals to n over Sn and Sn equals just 1. I just have these coordinates, and I know that only 1 is non-zero. Then I have to solve this problem first. Say this problem is a natural subproblem, is an easier problem as the first one, but I have to know how to solve it. So in a sense, I could ignore the fact that I have various blocks. I could say, okay, let's first concentrate on solving this problem. Then this prior I just gave is very natural because there is only one non-zero. So it's almost the same, the only prior you can construct. And then you say, well, in the general case, I just split in Sn block. But I agree that it is not completely straightforward to come up with this idea of splitting in Sn blocks. So maybe something that can make you think about it is that there is this Sn here. Okay, so if I can put this Sn, if I put on the other side, I have Sn times phi bar of B. So it suggests that maybe the overall difficulty is Sn times the difficulty in a certain problem, okay? And then the most natural problem is just indeed saying, okay, suppose I have just one non-zero and let me solve first this problem, okay? But it's a good question because actually for the large signal, which I didn't give the proof, so for the results on large signals, the least favorable priors in the sense that you use you also bound the min-max risk by a Bayes risk, but the priors you use there, they are not of this form. of the fact that you split the problem in essence subproblems. So, and I think you can't get any result by this approach in the other case. So, depending on the situation, it's kind of an art to come up with but generally it kind of, you can a posteriori kind of understand this. So I think that this prior here is kind of, one can understand it well by thinking in terms of sub-problems like this. Okay, so I think I'll stop here on the multiple testing and classification chapter. But you can see there are more details in the notes and even more in the paper. But so in the notes, I gave the proofs for the multiple testing risks. So as I said, the idea there is just to go to a weighted loss. Okay, questions? Okay, so let me then go to the last chapter, which is about variational approximations. So far we have, so the goal of the lectures was to give, like, one main goal was to give a set of tools to prove properties on posterior distributions that are useful for statistical inference. So we have seen tools for rates, for uncertainty quantifications with confidence sets, credible sets that can be proved to be confidence sets, and also testing in the last chapter. And now, so there is an aspect I didn't discuss much so far, is the aspect of computations, because in many practical problems, you would like to sample from the posterior, and so fortunately, there are many methods that are that people have developed in the last many years. So 30, 40 years at least. So one very popular class of methods is that of MCMC simulation method, so Markov chain Monte Carlo, where you construct a Markov chain whose stationary distribution is the posterior, and that's very popular. But there are other classes of algorithms, and in particular, variational methods are very popular, and especially recently, in particular in models where you have either a high dimensionality or high complexity. In particular, in these deep neural network settings, you have really a large dimensionality, a large number of parameters. The model is very complex, and MCMC method generally have may have trouble in scaling with the dimension. So in those type of settings, it's very popular to use a variational method. So what is the idea? So the idea is to approximate, so you have your target is the posterior distribution, you'd like to approximate it. Okay, so we'll use using a simpler family of distributions, which we'll call the variational class. Okay, and this will be the variational class, is this family of distributions. Okay, so that's the main idea, and the idea is really that the posterior can be a complex object. So we have seen even in this simple Gaussian sparse sequence model, we have, I mean, it's hard to be much simpler than this. I mean, you have this sparsity structure, but if you take, like, for instance, a spike and slab prior with, so you know, to take spike and slab with fixed alpha weight parameter, and then you draw alpha at random. For instance, you take a beta distribution. This is already a complex posteriors, because so although the posterior given alpha is a product, once you mix over the alphas, it becomes a mixture, a complicated mixture. So it's not at all independent. So in that case, you may think, okay, what if I would use a simpler family of distributions? So since this is complicated because I don't have independence over coordinates, I could assume, for instance, that coordinates are independent in my approximating family. And this is what is called Millfield type variational class. Okay? So there is going to be, of course, a trade-off between the complexity of the class and the computability. So I'll come back to that. So in terms of, although this type of methods are very much in use since quite a few years, the theoretical understanding is quite recent. So there have been 3 recent works around 2020 to understand in which sense the variational posterior, which I'll define in a moment, is doing something similar to the original posterior. And similar will mean that it has at least the same rate of convergence than as a posterior. Okay, so there is a work by Pierre here, and with his former student, so around 2020, work by Young, Bhattacharya, and Patti. And a work by Zhang and Gao. So here I'm going to present the approach by Zhang and Gao, although those papers are complementary and they share a little bit same type of, I mean, the general ideas are complementary and one can find some common kind of main ideas. So sorry, Pierre, I didn't know you were coming, but otherwise I would maybe have chosen your paper. While I was preparing, so those are results both for posteriors and for fractional posteriors as well. So, in fact, Zhang and Gao's paper is slightly more kind of in the spirit of classical posteriors. And for instance, Pierre's paper is also more in the direction of packed Bayesian ideas and for fractional posteriors. So they are really kind of interesting, 3 very interesting works. So I'll recall some definitions. Something I already defined is the Rényi divergence. I think I define it maybe only for rho between 0 and 1. So here, let me just do. I also need it for rho larger than 1. So for rho different from 1, the Rényi divergence is just we have seen it already with this log factor 1 over rho minus 1 log of the integral dp over dq to the power rho minus 1 dp. Okay, and if rho is 1, we define it as the Kullback-Leibler divergence. Okay. PQ, and in fact we can show that d rho goes to d1 as rho goes to 1. Okay, log q dp. Okay, so that will show frequently in the statements and proofs. And so let me define, so now I just gave the ideas, but so I mean the definition will be exactly what I wrote more or less. So we have a variational class, so just a collection of distributions, and we approximate the posterior distribution. We try to find the best, the closest element in this family to the posterior in a certain sense, and here it will be the Kullback-Leibler sense, but it could be also something else. But classically, so the variational posterior, well, perhaps I'll erase there. Okay. So the variational posterior Q hat is, so Q hat, the argmin over S. So if I have a collection of distribution S, so I think the argmin over S of the Kullback-Leibler between Q and the posterior. Okay. All right. So let me maybe just as a little side computation here, let me just write down. So recall that, so as usual, we'll work with a dominated model. Okay, so P theta in capital theta, and I have a dominating measure, so there are heads, which I'll sometimes forget, okay, for simplicity. And so d pi, we have base formula, so d pi of theta given x is going to be, so as given by base formula, P theta divided by, so here I introduce the density little p, so this is little p theta, P theta d mu, and let me just give a little bit of notation. So this here, the denominator I'll denote, so the marginal density of x. In the Bayesian setting, I'll denote dx as a shorthand. And so if I do the little computation, what is Q, the Kullback-Leibler between Q and the posterior? So it is just the integral, so the log of Q. So suppose I have also density little q for capital Q. Q theta divided by P theta x pi of theta times dx, and I integrate against Q theta d mu theta. Okay, and here you see that I can actually, so this quantity dx, it's not so easy to compute because it's an integral. It can be an integral over a high dimensional parameter space. So in general, it's difficult to compute this renormalizing constant, and that's also why there is all this all these algorithms like MCMC and ABC and others, because this is hard to compute in general. Okay, so what's nice is that this will split in two, so we can move the dx outside, and since Q is a distribution by definition. Okay, I have its integral is 1, so I have here plus log dx. Okay, so log dx is a quantity that doesn't depend on Q nor on theta. Okay, so it's independent of Q. Okay, so that's nice because in the optimization, so this is an optimization problem, so it can be solved by optimizing tools, which I will not talk much about. But you see that here you only need to minimize the first part, which doesn't depend, so it's an integral, but it doesn't depend on this one here, the renormalizing one for the posterior. Okay, so that's that's something one can note. Okay, so it's not completely trivial to okay, so there is a lot of literature on how to solve this problem, okay, this optimization problem, and I'll not enter into, so there are very interesting questions about, okay, are we close to a solution to this optimization problem, okay, but this is kind of separate, a separate question. So here I will assume that I have access, here assume that we have access to this optimizer, to Q hat, or it's enough actually to have access to a good enough approximation of Q hat, and then try to understand whether Q hat is a good object. So good will be in the sense, does it share the same, at least the same rate of convergence as the posterior? That's one possible question you can ask. Okay, so let me just formalize also a little bit the concept of mean field class. So assume, so suppose that the parameter theta, so for simplicity here, so since I want to do something product class, I will assume that the parameter is a product with possibly m is either an integer, but I also allow that m is infinity. Okay, so in the context of sequences, for instance, I have just one countable sequence. Okay, so the mean field class is the class of Q's such that Q is a product. Okay, so I assume that, so I approximate the posterior by distributions which are products. Okay, and I can be even a bit more specific, and I can, for instance, in the product, I can assume that Qj is Gaussian. Okay, so I can take the same, and Qj here being in a Gaussian class. Okay, so like n mu sigma square and mu and sigma are arbitrary. Okay, sigma square like this. Okay, so this is the mean field Gaussian class. Yes?
Maybe before you go further, I mean, okay, I understood that you are not focused in this chapter on solving the variational problem by itself, but maybe just a comment, because it's still a bit obscure for me. You say, okay, the posterior, it's so complicated that we cannot compute it.
So
I finish, but we are able to minimize the distance with this horrendous posterior, which seems a bit paradoxical, because you have this posterior, you do not know it, but you can know how you are approximating it. So I guess the solution is somewhere on the blackboard, but maybe it should be stressed why it's not as tough as it seems at first sight.
Indeed. So what happens is that so first one has to see that also the nature of the task is different here from the task, for instance, of MCMC, because MCMC, when you set for MCMC, you set for producing a distribution, so sampling a sampler which will sample something which hopefully is very close to the posterior. Okay, so you approximate the distribution. Here it's a problem of slightly different nature. We optimize. So in a sense, we want to find a minimizer. Okay. So indeed, it's true that at first sight, I agree that it's not completely obvious. So why this problem is much easier. Okay. So I tried to hint a little bit at why this may be a little bit easier just by telling you that, you know, you didn't have to compute this. So as I said before, one very big problem here is that you need to compute this guy if you would set to say, okay, I just want by brute force to compute the posterior, let me compute this is easy, and let me compute this, and this is hard. Okay. So I'll not enter much into the details of this, but indeed, this is a legitimate question, and they are, I mean, it's part of the, it will be, actually, I think it could be a whole lecture a bunch of lectures to explain what this problem, how you solve it, and why is it simpler. Okay, so I'll give a few references at the end on some, for instance, on the high-dimensional linear regression, where you can really see what people do in practice. Then they use some kind of coordinate updates. So you have, for instance, if you have Gaussians here, you can try to approximate this minimizer by updating coordinates, and then you have something that hopefully resembles to the optimizer here. But there are many interesting questions about, okay, so is this optimization problem solved in a sense? Because when you get, say, what you get is actually something like this, right? You don't get this. And really showing that this is close to this or that this has converged is a whole problem in itself. And so I'm not going to, I mean, it's a very interesting question, but it's kind of a bit separate from what I'm presenting here. But, yes?
Is there some cases which say that we should not use an approximation?
I guess so. So if you believe, for instance, that if you want to capture some interactions, you don't necessarily want to use mean field, because what you are going to lose, for instance, with mean field, if you think about this BVM theorems, for instance, that we showed before, is that so the Gaussian will always be here. So if we have Gaussians, for instance, it will always be of a diagonal form, right? Because by definition it's independent. So suppose you have a problem where you know that kind of this coefficient is very important. Of course, you may want to have like mean field. So if you suppose you want to capture the interaction between this and this, then maybe you'll have on this two by two block, you have a Gaussian, so you'll model actually here, instead of taking a product of m's, you'll isolate this 2 by 2 block, approximate it just by a general Gaussian, but with possibly a non-diagonal covariance matrix, and on the rest you do mean field, for instance. Okay, but that would be a case where you know, so because here by making it independent, you know that you force the independence, so that may not be good, indeed. Okay, so and there are kind of extreme cases. So here you could say, okay, let me take the class of all distributions, for instance. So it looks good, but of course the posterior belongs to it, and then. To go back to the earlier question, so in fact you have a problem of complexity, because if your class is too complex, actually you will end up with no gain computational. Okay. All right. So write it. So there is a trade-off. Okay, between the computational complexity, so which grows with say if we do a complex variational class, and also accuracy, okay, because if the class is too small, small class means that you have less approximation power. Okay. Okay. So, but mean field class is quite popular, and so let's keep it in mind as a main example. Okay. So now I'm going to state a generic result, which you'll see bears quite some similarity with the generic theorems we have seen in the first lectures. And so the idea will be to, so it turns out that one can relate the behavior of the optimizer Q hat to the behavior of the posterior itself, plus some extra conditions, and hopefully not too many extra conditions, and there will not be many more actually, which relate to the fact that we use a certain type of class. Okay. So the VB posterior, a bit informally, is just a Q hat. Okay. So the result will be expressed in a certain loss. So let L be a loss. So between. So we'll measure directly between the. So recall. So what we want to show is that the rate of convergence of Q hat towards theta naught, so will be as usual in the frequentist perspective, okay, frequentist analysis. So we assume that actually X, so we form this object and then we analyze it under the improbability under P theta naught. Okay, so we want to show that the rate of convergence to theta naught of Q hat is at least epsilon n if epsilon n is the rate of the posterior. Okay, so the result will be expressed as a loss between distributions. So we can think of many things. So the most so we'll have to be slightly careful about the normalization here because the loss will be directly on the full probability measures. So typically they will scale with n. Okay, so if we have IID data, for instance, and if your loss, say, is the Kullback loss, it will tensorize and you will get n times the loss for individual, if you have IID data for the individuals P theta naught. Okay, so that's why there will be an n, there will be some n factors showing. That's just the normalization. Okay, so here, for instance, something like this. If we have IID data. Okay, so that's a definition. Okay, I can define it like this: n times k p theta prime. Again, in this case, or I could also define just n times theta minus theta prime squared. Okay, so I could also divide by n here. So, okay, this would be directly the distance between parameters if we have it in a sequence setting, for instance. Okay, so that's just notation. There is nothing going on here yet. So the conditions are as follows. So T underlined will be something that you'll recognize as a testing condition. So except that here we just ask that it's true for any epsilon larger than epsilon n, which generally, if you know how to verify it for a given epsilon n, making epsilon big in general makes things often easier. So, but often it's not much more work to show that it works for any epsilon. So we assume that there exists some sieve sets that may depend on epsilon and some tests such that E theta naught phi n plus sup theta over the sieve sets of the distance. So here the distance is rather the loss. Okay, so it is very similar. It's almost the same condition as we had for the GGV theorem of the type 1 plus type 2 errors. This has to be exponentially small. Now in terms of epsilon, okay, so for any epsilon. So for GGV we had this, but it was for epsilon equals to epsilon n. Okay, so here I just assume it for any epsilon. You have to believe me that in general it's not much more work to show it. And then plus for the same for the sieve sets. So pi theta n epsilon complement is exponentially small. So the mass outside sieve sets is small. And finally, the prior mass. So here there will be no epsilon, just epsilon n for the prior mass. and we'll just, it's almost the same, it's just a little bit, so we remove this Kullback-Leibler neighborhood, we replace it by a Rényi type neighborhood with rho larger than 1. Okay, so P, the prior mass condition, there exists a rho such that by d rho p theta not n, p theta n, that this is at least, we put enough mass around the truth in this sense. Okay, so here there is constant C, so probability, sorry, I didn't define, so I have to write it because I didn't define the neighborhood, so let me, so the prior mass, so of the set of thetas such that d rho theta is smaller than C3 n epsilon n squared, so that's a neighborhood in the d rho sense of theta 0. This is larger than exponential minus C2 n epsilon n squared. Okay, so it's the same, essentially in spirit, it's the same spirit as the prior mass condition, but we formulate it in slightly different divergence. Okay, and the conclusion is that theorem, so suppose so n epsilon n squared larger than 1, and set let gamma n. So gamma n would be a quantity which will capture like the part of the problem that is related to the variational. So here it's in a sense it's a meta theorem because the statement still depends on the posterior. Okay, so but it's already simplified a bit. So this is a quantity that measures the infimum. So it almost like this, but there is an expectation, and there is still the posterior in there. So after this, I'll have to tell you how we bound this quantity. Okay, so suppose the previous conditions. Suppose T, S, and P hold, so you can, there's a little bit of tuning of the constants as before. Remember we had this 4 in the very early, in the generic GGV theorem, so here as well. So suppose these 3 conditions, then for a constant m large enough, which depends on the previous constants, C1, C, and rho, such that the E theta 0. So here, just a little notation, as I already did, I think before, Q of f is kind of the operator notation for integral f dq. So Q hat, it will just be the integral against Q hat, against the variational posterior of the loss. Okay, so what we want to control. Okay, this is smaller than m n epsilon n squared plus gamma n squared. Okay, and here we can maybe pause a little bit to comment on the result. So there are 2 rates. There is epsilon n squared, okay, epsilon n, and there is gamma n. So if you, I mean, by now we are familiar with these conditions testing sieves and prior mass, and so then actually we know that even by taking epsilon equals to epsilon n, okay, we do the fact that here I change a bit the neighborhood, we know that this will imply that the posterior itself converges at rate epsilon n. Okay, so epsilon n I should regard here as the rate of the posterior, and gamma n is more something like related to the behavior of the variational posterior, okay, of Q hat. Okay, and at the end we have a sum of 2 terms, and this will give an overall rate, so up to normalization by the n here, this will give an overall rate. This gives rate epsilon n squared for q hat as soon as I am able to bound gamma n squared by epsilon n squared up to a constant. Okay, so we still need to work to understand this term better. Okay. Yes.
Can you explain what does that mean? This expression because you wrote q hat and
Yes. So this is this notation. So q hat of a function of theta is just a short notation for the integral of f theta dq theta. Yeah. It's just.
I have another question.
Yes.
As regards the sieve condition,
Yes.
just why do we want to call it sieve? Sieve is cube en anglais? Is that
Yeah, in French, I think it would be tamis or something like this. So it is just, you can view it just as a smaller set than the whole, the full parameter set. And the purpose is just to simplify the analysis, to say that I only need to work on this subset and I don't have to care of what happens. So, you know, in R, for instance, a typical case of choice of sieve is just a compact interval that may grow with n, but where you throw away. So instead of taking R, you take, I don't know, minus square root n, square root n. Or, so it's just something that removes some part of the parameter set which would make the complexity too big.
and the name sieve?
Right, exactly. So it's really the same condition, except that I assume that it's true for any epsilon larger than. But it's really the same in spirit as we had before. And in fact, if you don't like this condition, you can remember that we had also the results for fractional posteriors that didn't require these first two conditions. And there, in fact, you can prove similar results for fractional posteriors as well. Okay, with true posterior, classical posteriors, we have this. Yes, yes.
Just to try to compare with the previous result with the GGV or GGV with the fractional posteriors, do you have concentration of the posterior mass in this situation?
Yes, yes. Yes.
0 is rho bigger than 1.
Yes, yes. So I'll write it in a second. In fact, with these conditions, you have an even more precise result. You have concentration at rate epsilon n of the posterior, but you even have a bit more. So with the fact that you have for all epsilon and the fact that you put rho larger than 1, you have a bit more, and in particular you have exponential decrease of the posterior mass outside the neighborhood in expectation. You have I'll state that in a moment, that what you have. But indeed, so it already gives concentration of the posterior at rate epsilon n, and it kind of decouples the two problems here. One is the rate of the posterior, and then the contribution of variational is here, and the goal is then now to prove this. Okay, more questions? Okay, so to control, so okay, write it here. So controlling gamma n now. So now I'll bound, so there is a little lemma that shows that gamma n squared is smaller than a quantity that now doesn't depend on the posterior. So inf over q of two parts, so the Kullback-Leibler between q and the prior, not the posterior, plus q, again in this operator notation, q k p theta naught n p theta n. Okay. All right. So let us check that, and so then we'll have then a sufficient condition for verifying this can more easily be expressed in terms of just the prior by controlling this. Okay. So let's prove this. So that would be lemma 1. So I'll introduce here some notation and maybe do the proof on the other side. So notation as shorthand for the posterior, I just note p dot x. I'll give a notation for the marginal, so it's it's still on the board. So here, as usual, it's a little p. Okay, that is the marginal density of capital X, and I'll just give a name for the distribution associated to it. It's just that when I write the Kullbacks, I can just use distributions instead of densities, but it's not very important. So here is capital P. Okay, and so the density of this is just this here with the small p instead of the capital P here. Okay, and base formula is then given by just in this notation, it's just dpx equals to p theta n d pi over the normalizing factor, which is then so here I've put everything in big, so here it's big P also. No, so sorry, small p here because it's the denominator. P pi of n. Okay, so that's base formula. All right, and now we can write this quantity here. So let's rewrite the Kullback. Okay, so the Kullback-Leibler divergence between Q and pi x. So let me just write it as, so that by definition, dq over d by x dq, and d by x I itself wrote as, I separate in 2 bits, okay? Integral of log dq over, now I'll put d pi here, dq, plus what remains is I get a ratio of so log of p theta p pi, okay, p theta n p pi dq. Okay. All right. So now I can take also the expectation. Take the expectation here. Right, so what is the expectation of this quantity? E theta naught, E theta naught, E theta naught. So here it doesn't depend on the data. So here I can remove it. Okay, so this is just Q, the Kullback-Leibler between Q and pi. So that's great. That's the first term. And now the second term. Okay, so this term right here. So what is this? I again divide a little bit. I again split the. So I can use first Fubini to pull the expectation inside. Okay, get E theta 0 log p pi over p theta n. Okay, and then dq. Okay, which I can rewrite in my operator notation, q of something, right? And then here I again split in 2, so that here is the integral dp theta naught. So I can write it as integral log d pi over dp theta naught. Okay, so let me maybe just write this. So this I can rewrite the expectation that theta naught. I just expand inside the integral. It just the integral of log d pi over dp theta dp theta naught. Okay, so I get something like this. So here I think I mixed a little bit the notation. So it's d p pi, sorry. D p pi, which is the marginal density of x, not pi. Pi, we have already dealt with it, it's here. Okay, so dp, here I introduced instead of theta, I put theta naught. So I have to compensate for it now, plus integral log d pi theta naught now over d pi theta. Okay, d pi theta naught. Okay. And so here I recognize on the right hand side I'll get the Kullback that is over there. Okay. So this is just Kullback p theta naught p theta. And here I have something which is minus the Kullback of p theta naught p pi. Okay. So as the Kullback is positive, is a non-negative quantity, I have with the minus I have smaller here. So I get, I then get that this is smaller than q k p theta naught p theta, and we are done because that's what we wanted to show. Okay, that the gamma n squared is smaller than this. Okay, so so far so good. So then just a little implication. So let me maybe let it here. Of this is that if now we have, so now I'll set just a sufficient condition for verifying this, and it will just be that that both terms, condition guaranteeing that both terms are here in this sum are smaller than epsilon n squared. So corollary. So we get that under conditions of theorem 1, so E script denote the set of distributions that are supported, that have the support inside included the set of theta such that the Kullback-Leibler, so the second term is under control, the inside of the second term is under control. Okay, so p theta naught. So here I kept the n because since I have a bit some n's everywhere with the normalization, I find it always helpful here to keep the n. Okay, so the definition, and suppose that I can find, so the infimum over the variational class and the set of distributions that verify this property, that I can find then therefore certain element of the variational class that verifies both this and that its Kullback-Leibler to the prior is not too large. So here you see we don't need to be super precise, right? So we don't need an extremely fast rate. So of course you can think that maybe there is still the normalization, right, with the n, but we don't need something that goes extremely fast here to 0. We just need this. So under these conditions, then we get this. So the goal, this with epsilon n squared plus gamma n squared, which is of the order epsilon n squared. Okay, so which is what we want. Okay, so that's nice. And then let me give you immediately some application to the mean field class, just to see that this can be, in principle, one will have relatively easy conditions, and indeed they will be easy, particularly if the prior happens to be in your variational class. Okay, so if you think, for instance, of spike and slab priors, so if your prior is spike and slab or of subset selection type, you may choose still a spike and slab type class. A spike and slab class is really a mean field class, okay? So because it's just a product, so it falls into the mean field class, and then in that result that I'm going to state now, you you can take actually the prior as an element of your variational class. So this will simplify a bit the condition. So case of mean field class. Okay, so let's look a little bit at what happens there, and then I'll turn to some ideas of the sketch of proof of theorem 1. Okay, so theorem 2. So suppose we have a mean field class, this mean field, and conditions of theorem 1 are met. Okay. Suppose that there exists and there exists a Q tilde in the mean field class, as well as some product type sets. So it's natural because we work with mean field, so we'd like to express things like prior mass conditions in terms of just products. So let's do that. So suppose there exists an element Q tilde of the mean field class and sets which are of product forms with the elements being some theta tildes included in so that the whole thing is included in theta, such that two things hold. So the first one is that this product set should be included in a sort of Kullback-Leibler type neighborhood again, but with an extra little term, which I'll write in a second. So the first bit is just like Kullback-Leibler. So the Kullback-Leibler should be smaller than C1 n epsilon n squared. So that's a bit as usual, I would say. And then plus, so not plus, but and dq tilde over d pi. So the density, the log of the density should be controlled by C2. So this is a set of thetas so that these two conditions hold. So the Kullback-Leibler between the truth and the candidate theta is under control, and the log of the density ratio of q tilde and pi at point theta is controlled by the same type of quantity. Okay, so this is one condition, and the other condition, B, is that we want q tilde of am, so that's like a prior mass, but for a q, is larger than these usual exponentials. Okay, like this, and if this holds, then we have that gamma n squared is smaller than the sum of the constants that came in before times epsilon n squared. Okay, so in particular we get square. Okay, which is what we want with okay, epsilon n squared plus gamma n squared smaller than epsilon n squared. Okay. So here we get a set of conditions that still look quite familiar, right? So, and that's where the structure of the mean field class gets mixed with the model and the prior. And suppose that, so in the case, so if pi, a remark is that if pi belongs to the mean field class, we may take, why not, as long as it verifies the other conditions, q tilde equals pi. Okay? And if q tilde equals pi, then this, you don't even have this. Okay? All right, and then, so you see that instead of having here a sort of prior mass condition in terms of the usual quantities, we like more the Kullback-Leibler neighborhood, we have it in terms of certain subsets which respect the structure of the variational class, namely that are of product form themselves. Okay, so let me see. So what we have to choose now, either, I mean, I can give the proof is not very long, but yes?
I should have a question. So in the whole approximation process, if you have a posterior which has very dependent marginals, then whatever you do, you're not going to be able to converge, right?
So, I mean, yes, so if the posterior is extremely complex and very dependent, you may think that, you maybe can find cases where you'll have something which is very bad, okay? So the idea here is that even if, so in general, this, however, the mean field class is still quite powerful because it will, if you take like in any problem where you imagine that you have a posterior and just take replace it by the product of marginals, if in that case this object may still converge, right? So and in many examples actually we have still the same rate of convergence, except that the covariance is worse. So essentially you lose in the constants because of this mean field class. But still, even so, for instance, one example I'm going to give next a bit later is the high dimensional regression. Even there, where you have many dependencies, still the class of product distributions over coordinates is rich enough so that you get the rate epsilon n squared. Okay.
And so, where is the assumption that assumes this? Because somehow it's hidden that the product of the marginals is sufficient.
Well, so it's so you know it will be here in this for instance, if you take the mean field in this result, so that's here that you have the what's going on, because you get the rate. So for the variation, that is kind of the contribution of the variational. So here it's I would say it's really here that you get this type of conditions, right? So if you are able to satisfy this, then it will work. Yeah. So so you know, so I mean it's so how can I put this? So so if you imagine, for instance, that you are in high dimensional regression, the kind of a trivial candidate approximation of the posterior, that's not what you want to do in practice, but just as a thought, kind of a thought experiment. So suppose you have an estimator like, I don't know, the posterior mean or the lasso or a good estimator. You could consider just a product of Dirac masses at the components of this estimator. This is in the mean field class, right? And this object is still good in terms of convergence because okay, it's well centered. But of course, you completely lose all the rest, the fact that it's a distribution, right? So I agree that, so in a sense, it's a good question because here the result I show, so ideally what you'd like to understand is how the variational posterior, how it relates to the posterior as a distribution itself. Here we just look at some very specific aspects which are kind of projections, just a rate. But you know, you could have distributions that are like, so like this, or you know, like this. So if I compare this distribution to this one, okay, so suppose it's a posterior, and here, so you know, they are very different, but they are still good for the rate. So here I didn't tell you that I'm comparing pi tilde of x to pi of x, or here in our notation it's q, say, q hat, okay. I'm not saying that q hat resembles pi the posterior, right? So I'm just saying that it converges at least at the same rate, okay? But ideally, what you'd like to do, and that's also some, I guess, also some interesting questions in this area, is to try to say more about this. So can we say that the variational posterior resembles the posterior in that, for instance, it has either similar instantaneous modification or similar model selection properties? Like in high dimensional regression, you may want in particular to have like yesterday we did testing, okay? So it's very important to have access to these quantities, okay? And that's very hard. So in high dimensional regression, it's hard to compute this. For the variational, it's easy to compute this. But to my knowledge, there is no result saying that you know, the variational analog of this is close to this, okay? So in other words, it gives some promising results saying that you know, the variational object converges at the same rate, but it doesn't yet give you that it is close in some sense to all the aspects of the object you approximate. Okay, that's a good point. So let me maybe, so the proof of this is so in the notes, actually, I haven't put proof yet. I didn't have time to write it down, but it's either in the paper, but I will fill in also this in the notes. The proof is really just a few lines. You just combine the different definitions a little bit as we did before. But I think I'll maybe spend a few minutes in giving a sketch of proof of theorem 1, and then give the example of high-dimensional linear regression. Okay, so proof of the main theorem. So the key, there are two key lemmas. So one lemma 8.3. This is just at first sight, I mean, it's again a lemma combining a little bit different quantities. So you have an integral, so Q in my operator notation, QF, integral f dq. So this is smaller than Q, the Kullback between P and Q, plus log integral fx d pi of x. Okay, and so why do we use this lemma? So let me state straight a different yet another lemma. So I think it's 8.2 maybe in the notes. So it says that what we want to control in theorem 1 is the expectation on the theta naught of Q acting on the loss. Okay, and this is smaller than the infimum over A, positive of 1 over A. And then we have two quantities that kind of show up, appear in the theorem. So we have this part which gives rise to the gamma square plus log of integral of exponential. So that's where we are going to need this kind of strengthening of the GGV result, because we need exponential tails here, at least in the way the proof is done. But we get that by the slight strengthening of the conditions of the GGV theorem. Okay. Great. So in theorem 1, this is what we want to control. This will give you the gamma n squared, and this is something related to the posterior that hopefully will give us, will be the epsilon n squared part, okay? Because recall in theorem 1 we have these two parts, the part relative to the posterior and the part relative to the variational class, the approximation family, okay? Which is the gamma n encoded by this gamma n squared. Okay, so let's prove this. Okay, so let's start with lemma 1. So the lemma, well, the first lemma on the board. Okay, so this is again a manipulation of Kullback. So proof of this lemma. So here we just write, so if I have, if I denote this by Cf, so that's a constant that depends on f. So I have that the Kullback Q, so is that Qp rather, sorry. Qp. So the Kullback Qp plus Cf, so by definition it's the integral of log dq over dp dq plus Cf, okay? And Cf I can write integral Cf dq because it's a constant, doesn't depend on q. Okay, and now I'm going to introduce this constant inside here. So it's log dq over dp e to the Cf. Okay, so I can actually directly write it as the integral e to the Cf is just the integral of f exponential f dp. Okay, dq plus, that's it. There is no plus, I put it inside. So now I'll just put here e to the f inside and outside, e to the f. Okay, and now I can form the tilted measure here. Okay, so exponential type tilting sort of. So I have EF dp, and I normalize it. So I divide it by the normalizing factor, which should be the integral of EF dp. Okay, and dq plus, so, well, let me still write this. What I have here is that I have to compensate. Okay, so I have the well, here it's already written, so okay, don't need it, plus, so I'll pull this EF outside, so log of EF is just f. Okay, so here I get plus f dq. And since this is a Kullback, okay, it's a Kullback, so it's positive. So this is, what I get is that this is larger than integral f dq, which is what we wanted. Okay? All right, and now, so let's, for this lemma, we just apply the previous result to, actually, so apply lemma 8.3 with what? So with just the q hat is going to play the role of q. Q hat to q equals q hat. P equals the posterior. Okay, and f theta, the function f theta is just a times the loss. Okay, p theta not. Okay, and then and A is just a constant. Okay, so if I do that, I essentially get this. So the only thing I need to do is, and maybe I forgot it. So let me see if I forgot this in the statement. Yes, I think I forgot it. Sorry, I forgot an expectation here. Log E theta naught. But it's not very difficult because now, so if we apply this lemma, we get the thing with the q hat without the expectation. And then we take the expectation and we just pull this inside plus the apply Jensen with the logarithm to pull the expectation inside, okay? Put the expectation here and then we get the result, okay? Because this still depends on the data, so therefore I need an expectation here. Okay, and now, well, to conclude the proof, it's enough to do two things, which I'll not do in details, but the first is that under these conditions of test, sieve, and prior mass, you get the conclusion of GGV, but strengthened to have exponential tails. Okay, so that's not very difficult. It's kind of an extension, a nice extension of GGV. I told you there were many kind of refinements. This is one of them. And once you have exponential tails, you only need to see that, so if you have a variable with like something like this, okay, minus AT, this will imply that you have a control of some Laplace transforms, not all, but the Laplace transform of it will be under control, okay, with B sufficiently small. And therefore, here you have something which is really like a Laplace transform, so you only need to apply, I mean, I'm skipping a few details, but that's the essential idea. Once you have an exponential decrease of this, then you can just use this to have the control also of the exponential moment, okay? Because here you need an exponential moment. All right, and then this gives you something in terms of epsilon n, okay? Because GGV gives you the posterior rate, epsilon n squared, and the gamma n squared bit is captured here, okay? So that gives you the proof. All right, so maybe very quickly, in maybe 2 minutes, let me just give you a result on high-dimensional linear regression. So that's a recent interesting work by, very nice work by Kolian Ray and Boton Sabo. And also with the, okay, so recall the model x theta plus epsilon. We are in high dimensions, so p can be much bigger than n. And there is also a nice package, package written in particular by Gabriel with Ren and with Kolian and Boton. So the R package, which does linear regression and logistic regression, is called sparse VB. Okay, so there you just put the prior on theta will be of spike and slab, hierarchical base spike and slab. Okay, so you do theta given alpha is spike and slab. And here you do, for instance, you can take a beta. So you need slightly more than this 1 and plus 1 that we took for the sequence model. We take p to the power b with b strictly larger than 1, just to penalize a little bit more the high dimensions. And here you take spike and slab just with Laplace 1 slab. Okay, and with weight parameter alpha. And for the class, variational class, you take the mean field class, a mean field class of spike and slab form, except that for computational reasons here it's simpler to work with Gaussian slabs in the variation class. So it's important to realize that you don't want to put Gaussian slabs in the prior class, because we have seen that Gaussian is not good as a slab in high dimensions, unless you want to have some strong assumptions. So, but in the variational class, there is no reason. I mean, you can put Gaussian. That's no problem, because it's approximating the posterior. So if the posterior is good, that should be fine. Okay, but you need to ensure it's good. You need at least Laplace tails for the slab. So as usual, take so pi tilde, which I denoted q hat. I mean, our q hat is the argmin as before. Okay, q pi dot given x, argmin over q. Then you get theorem is that you get rate for q hat, which is the following. You get that e theta naught pi tilde, so in L2 loss larger than some mn. So here, to fix IDs, I just take this x, I take IID Gaussian components. Okay, so xij's, I'll take IID Gaussian, not to have too complicated assumptions. And here I get the optimal rate for this case up to the form of the log factor. Here goes to infinity goes to 0, sorry, for mn arbitrary going to infinity, so as slow as you wish. Okay, so you get the same rate as the posterior, and you have something that you can compute very efficiently. So the air package works for fairly large n and p's. Okay, so sorry for going slightly over time. Thank you very much. So thank you for being there, and I enjoyed a lot all the questions and discussions, so it was a pleasure. So thank you again. Yes?
So in the notes it's written that this last statement works with overwhelming.
Yes, I forgot to say that. Yeah, thanks. So here I took, so when you work with the high dimensional linear regression, there are two options for the x. Either it's deterministic, or sometimes one assumes that it's random, and it makes actually life simpler, because then you have more structure. And the easiest assumption you can think of is IID Gaussian design. And with IID Gaussian design, so you're right, I forgot this. So this is with high probability with respect to x. So on an event of high probability with respect to the law of x, you'll have that x verified this compatibility condition, this eigenvalue type conditions that I gave when I talked about high dimensional linear regression. I told you that since p can be larger than n, this is not identifiable, so you need to assume things on x. And here we assume, of course, that so theta is sparse, so you need to know that on sparse subsets you can invert. And this is true with high probability for this matrix. And actually, I forgot here to mention there is a little condition here on S to ensure this. So thanks for the question. You need some condition on Sn. I mean, actually, it's not completely necessary, but I think I stated like this in the notes. Right, so you need something on x, and indeed either x is fixed or it's random, but then you work on an event of high probability on which you have enough local invertibility of the x. Yeah, thank you. More questions? Can have coffee. Thank you again.